Good day, everyone. Welcome back to my channel. Again, this is 16Garlitos from BSED Math 3P. So now, we are going to explore cyclic group and subgroup. So we are going to use the subgroups that we have explored from the previous project. Also, in this project, we will integrate the subgroups and explore all the cyclic subgroups they have. To do all of those, let us first have a quick recap about the definition of a cyclic. So, cyclic or cyclic group is a cyclic group. It is a group that can be generated by a single element. So this also means that the elements of a group can be generated by one of its elements under binary operation or the operation that will be used by it. So it just means that under a group, when you get one of the elements of that group and you perform a cyclic operation under that binary operation, and if it generates all of the elements under that certain groups that where it came from, then it means that the group is cyclic or cyclic. So now that we know what is a cyclic or a cyclic group, we will now determine if the group of pink aurora algebra is a group that we will is pink aurora algebra is a cyclic subgroup, and we will also check if its subgroups are cyclic subgroups. So let's start with the improper subgroups up to the trivial subgroup, just like the flow that we followed from the previous project. So let's go. So this one, we need to determine if the improper subgroup, the P sub 13, is cyclic. So this is the improper subgroup, right? This is the table of the results of the improper subgroup. So now consider the improper subgroup P sub 13, which is the set of MILESGAR 1, 2, 3, 4, 5, 6, 7, 8 under binary operation star. So this is what we do to determine the elements that can be generated from that element. So here we do the M, which is going to be the M star M, and M would be the outcome. So the twist is when it generated itself again, that certain element generates itself again, that would be the end of the set, or that would be the end of the element generation, or how the elements are generated. So you go with I. So first we have the I star I is L, L then which is in here. Now we go with L star I. L star I now it'd be E. So that is E. Then S star I is G. So that is the G in here. And then G star I is A. So that is the A. Now A star I would be R. That is the R. Then R star I is M. With M. Now the M star I is I. So that is the end of this set that is generated by the element I. So that goes, or same goes to all of the elements up until the trivial subgroups that we have. So let's check. So for L, we have generated the elements of S, A, M, L. For the element E, we have generated the elements of A, I, S, R, L, G, M, E. For the element of S, we have generated M and S. For the element of G, we have generated L, R, E, M, G. For the element of A, we have generated S, L, M, A. For the element of R, we have generated A, G, A, S, E, L, I, M, R. For the element of 1, we generated M1. Element of 2, we generated M2. Element of 3, we generated M3. Element of 4, we generated M4. Element of 5, we generated M5. Element of 6, we generated M6. Element of 7, we generated M7. And lastly, element of 8, we generated M and 8. So now we need to determine if the improper subgroup P sub 13 is cyclic. So based on the elements of the improper subgroup, no element has generated the whole group. Because of this, we can conclude that the improper subgroup is not a cyclic subgroup. So based from these um, elements, we have generated only limited elements, and it does not show all of these elements under P sub 13. So this we can conclude that it is not a cyclic subgroup. cyclic subgroup. So determine if the proper subgroup P sub 1 is cyclic. So consider the subgroup P sub 1, which is the set of M and S under binary operation star. So for M, we generated M. For element of S, we generated M. S now is proper subgroup P sub 1 a cyclic subgroup. So based on the of the proper subgroup, an element has generated the whole group. Because of this, we can conclude that the proper subgroup is a cyclic subgroup. So we can see it in here that in the element S, it generated both the elements under P sub 1. So that means that it is a cyclic subgroup. So determine if the proper subgroup P sub 2 is cyclic. So consider the subgroup P sub 2, which is the set of M1 under binary star, and we can have the M generates M and 1 generates M1. Now is proper subgroup P sub 2 a cyclic subgroup? So based on the elements of the proper subgroup, an element has generated the whole group. Because of this, we can conclude that the proper subgroup is a cyclic subgroup. So yes, we can see that the element of 1 generated both the elements under the proper subgroup P sub 2. Therefore, we can say that it is indeed a cyclic subgroup. Next, determine if the proper subgroup P sub 3 is cyclic. So consider the proper subgroup P sub 3, which is the set of M2 under the binary operation star. Now we have the M generates M and then the 2 generates M2. Now is the proper subgroup P sub 3 a cyclic subgroup? So based on the elements of the proper group, an element has generated the whole group. Because of this, we can conclude that the proper subgroup is a cyclic subgroup. As you can see in here that the element 2 generated both the elements under the proper subgroup P sub 3. So by that, we can say that the proper subgroup P sub 3 is a cyclic subgroup. Next one is determine if the proper P sub 4 is cyclic. So consider the proper subgroup P sub 4, which of M3 under binary operation star. We have M generate M and then 3 generate M and then 3. Now, based on the elements of the proper subgroup, an element has generated the whole group. Because of this, we can conclude that the proper subgroup is a cyclic subgroup. As you can see, the 3 generated both the elements under P sub 4. So by that, it is an indication that the proper subgroup P sub 4 is a cyclic subgroup. Next, determine if the proper subgroup P sub 5 is cyclic. Consider the proper subgroup P sub 5, which is the set of M4 under binary operation star. M generates M and then 4 generates M4. Based on the elements of the proper subgroup, an element has generated the whole group. Because of this, you can conclude that the proper subgroup is a cyclic subgroup. Determine if the proper subgroup P sub 6 is cyclic. Consider the proper subgroup P sub 6, which is the element of M and 5 under binary operation star. M generates M, 5 generates M, and 5. So based on the based on the elements of the proper subgroup, an element has generated the whole group. Because of this, we can conclude that the proper subgroup is a cyclic subgroup. Yes, we can see in here that the element 5 generated both of the elements under the proper subgroup P sub 6. And through this, it is an indication that it is a group since an element has generated both since an element has generated all the elements under its subgroup. Next, determine if the proper subgroup P sub 7 is cyclic. Consider the proper subgroup P sub 7, which is the set of M and 6 under binary operation star. M generates M, 6 generates M, and 6. Based on the elements of the proper subgroup, an element has generated the whole group. Because of this, we can conclude that the proper subgroup is a cyclic subgroup. Determine if the proper subgroup P sub 8 is cyclic. Consider the proper subgroup P sub 8, which is the element of M and 7 under binary operation star. M generates M, 7 generates M, and 7. Based on the elements of the proper subgroup, an element has generated the whole group. Because of this, we can conclude that the proper subgroup is a cyclic subgroup. Now determine if the proper subgroup P sub 9 is cyclic. Consider the proper subgroup P sub 9, which is the set of M and 8 under binary operation star. M generates M, 8 generates M, and 8. Based on the elements of the proper subgroup, an element has generated the whole group. Because of this, we can conclude that the proper subgroup is a cyclic subgroup. Determine if the proper subgroup P sub 10 is cyclic. Consider the proper subgroup P sub 10, which is the element of which is the set of M, R, A, G, S, E, L, I under binary operation star. M generates M, R generates A, G, S, E, L, I, M, R. A generates S, L, M, A. G generates L, R, E, M, G. S generates M and S. E generates A S R L G M E. L generates S A M L. I generates L E S G A R M I. So, based on the elements of the proper subgroup, there are elements that generated the whole group. Because of this, we can conclude that the proper subgroup is a cyclic subgroup. Yes, we can see in here that the elements of R, E, and I generated all the groups based from the outcomes of their cyclic operation. Now determine if the proper subgroup P sub 11 is cyclic. So consider the proper subgroup P sub 11, which is the set of M S 15 under binary operation star. We have M generates M, S generates M and S, 1 generates M1, and 5 generates M5. And based on the elements of the proper subgroup P sub 11, there is no element that generated the whole group. Because of this, we can conclude that the proper subgroup is not a cyclic subgroup. So we can see in here that all the elements did not generate the whole group. They only generated one or two elements under their cyclic operation. So therefore, it is an indication that this P sub 11 proper subgroup is not a cyclic subgroup. So determine if the proper subgroup P sub 14 is cyclic. So consider the proper subgroup P sub 14, which is the set of MASL under binary operation star. We have M, which is M which generates M, A generates S, L, M, A, S generates M and S, and L generates S, A, M, L. So based on the elements of the proper subgroup, there are elements that generated the whole group. Because of this, we can conclude that the proper subgroup is a cyclic subgroup. We can also see it in here that the elements A and L generated all the elements under P sub 14. So this is an indication that P sub 14 is a cyclic subgroup. Now, determine if the trivial subgroup P sub 12 is cyclic. So consider the trivial subgroup P sub 12, which is the set of M under binary operation star, and M generates M. So based on the elements of the trivial subgroup, there's an element that generated the whole group. Because of this, we can conclude that the trivial subgroup is a cyclic subgroup. Yes, we can see in here that the element M generated itself. So therefore, it is a cyclic trivial subgroup because it generated the whole group under the trivial subgroup P sub 12. So this is the analysis that we can conclude based on our cyclic group and cyclic subgroup. Among all the subgroups of the pink aurora algebra, only two subgroups are not considered cyclic. And the subgroups that are not cyclic are the uh, RD group RD proper subgroup P sub 11, which is the set of S15 under binary operation star, and the improper subgroup of P sub 13, which is the set of MILESGAR 1, 2, 3, 4, 5, 6, 7, 8 under binary operation star. So therefore, we can conclude that P sub 11 and P sub 13 are the subgroups that are not cyclic under the pink aurora algebra. So again, this is Milecent Garlitos from BSN Math 3B. Thank you for watching my video and thank you for listening. Goodbye!